Hi everyone, in this video we are going to be discussing optical activity. Now, we're going to say that a molecule that is optically active is chiral, and what this optical activity refers to is that chiral molecules can rotate the plane of polarized light. Okay, so optical activity refers to this ability for a chiral molecule to rotate plane polarized light. If you were to hit the compound with a beam of plane polarized light, which has a specific directionality, that chiral molecule would rotate the light to a specific numerical degree, either clockwise or counterclockwise, and that really depends upon the compound. The optical activity of each compound can differ, okay? Now, what's interesting here is that enantiomers will rotate plane polarized light in the opposite direction to the same degree. That is to say, if you had a pair of enantiomers, we're going to assign arbitrary optical rotation. Maybe S rotates light plus 27 degrees, clockwise 27 degrees. That means its enantiomer would rotate light negative 27 degrees, counterclockwise negative 27, okay? So if a molecule is chiral, it will rotate the plane of polarized light, and the optical activity can differ per molecule, but we can make a statement about enantiomers. Their optical activity will be opposite in terms of magnitude, okay, clockwise, counterclockwise, but in terms of numerical value, it will be the same, okay? Now, another aspect of this optical activity is that it has to be determined experimentally, okay? Like if I just told you that a compound had the R configuration, there was one asymmetric center, you wouldn't know if it rotates light plus versus minus. That has to be determined via a process called polarimetry, okay? Now, polarimetry just is this process of essentially dissolving the compound in a solution and having this little device that would measure the optical activity, okay? Now, if we discerned that R rotated light minus 42 degrees, then we know that its enantiomer, which has the S configuration, would rotate light plus 42 degrees, okay? And let's say you had a solution. We're going to say this is maybe compound X, and we have XR and XS. If you had compound XR and compound XS in solution in a 50-50 ratio, okay? 50% R, 50% S, we call that racemic. That means we have equal parts of R and S, equal parts of enantiomers in the solution. And if you consider the optical activity of the solution, it would be 0. The solution overall would be optically inactive. Why? Because we have equal parts R and S, and they are rotating light in opposite directions, canceling each other out. If there was an excess of 1, the overall solution would have an optical activity, okay? If you just had a solution of 1, a pure enantiomer, a single enantiomer, say R, it would be negative 42 degrees in terms of its optical activity, okay? Now, molecules that are not chiral, molecules that are achiral, will be considered optically inactive. It is the case that if a molecule does not have a non-superimposable mirror image, their mirror image is superimposable, okay? The molecule is achiral, and it is optically inactive. It will not rotate the plane of polarized light. Now, another thing that I want to do real quick is throw in these terms dextrorotatory and levorotatory. Okay, I'll probably botch the spelling, but it's dextrorotatory. Again, I apologize if I botch the spelling. We have dextrorotatory and levorotatory. Okay, dextrorotatory is essentially rotating light clockwise plus, and levorotatory is referring to rotating light negative, which is counterclockwise, okay? So we would say over here, our example S was dextrorotatory, and over here we have levorotatory, all right? So again, if you just were told that a compound had certain configurations, you don't know if it's dextrorotatory or levorotatory, plus or minus. That has to be experimentally determined via polarimetry, all right? But if we know the optical activity of one enantiomer, we can make a statement about its other non-superimposable mirror image partner, its enantiomer. All right. Now, I know we talked about diastereomers before, and the interesting thing about diastereomers is their optical activity will be different. okay, in terms of numerical value. It could also be different in terms of plus versus minus rotation of light. But enantiomers will have numerical opposites, all right? Plus 27 versus minus 27, for example. Diastereomers, their optical rotation value will differ, okay? Now, I want you to be familiar with saying that optically active means chiral. Optically inactive means achiral. You will probably be asked questions about, is this molecule chiral? But you could also be asked, is this molecule optically active? And optically active is saying the molecule is chiral. If a molecule is optically inactive, the molecule is achiral. Okay, multiple ways to ask the same question. You should be familiar with this idea of optical activity and this idea of polarimetry, the terms dextrorotatory and levorotatory, and the corresponding plus versus minus designation that we give to each of those rotations of light.